Now let's start studying the Poisson distribution. Let us give the definition first. So this k is a random variable that can take the value from 0, 1, 2, 3, and so on. So no negative integers. Then, if this random variable follows this distribution given by this function, then we say this random variable follows the Poisson distribution with parameter mu. So here we have parameters in two places, so both are mu. Okay, it's a Greek letter. And we write k follows Poisson distribution with parameter mu. Okay. By the way, the pronunciation of this word is not Poisson, it's Poisson. It's a French word. Okay. Now, Poisson distribution is often used for modeling the number of occurrences of some rare phenomena. Okay. And in fact, this distribution can be derived from the binomial distribution in some limit. Okay. Let's say instead of, for the moment, let's forget about Poisson distribution and let's consider a binomial distribution. So suppose k follows binomial distribution with parameters n and p. Okay, so the probability mass function is given by this. So, and choose k, p to the power of k, 1 minus p to the n minus k. So that is just this, k factorial, n minus k factorial, and pk 1 minus pn minus k. Now, let's expand. Again, what do we see? Okay, so let's expand these factorials, and we can cancel some part of n factorial with n minus k factorial. Okay, so that would be n minus 1, n minus 2, up to down to n minus k plus 1, and k factorial is still here. So the remaining terms are cancelled by this one, n minus k factorial. Okay, and also we put p equal to mu over n. Okay, just change the variables. Okay, so in place of p we have mu over n to the power of k, and 1 minus mu over n to the power of n minus k. Okay, now, so in this factor we have k n to the power of k. So there are n k's here. So let's move this one out, and also here we have actually k terms here, right? n minus 1, n minus 2, up to n minus 1 plus k. So there are k factors in the numerator. So for each of these factors, we assign one of these n's. So we have n, this n, and this one of these n's, and n minus 1, n, n minus 2, n, and down to n minus k plus 1 over n. Okay, and we are left with this mu to the power of k, and we have this k factorial here, and we still have, let's see, 1 minus mu and n minus k. Okay. Alright, let's split this one into two parts. So this is n minus n minus n up to n minus k plus 1 n mu to the power of k, k prime, 1 minus mu over n to the power of n times 1 minus mu minus k. Okay. Now, remember this one? So, from here, we have mu equal to np. Okay, let's keep this mu constant, but we move n to infinity. So since mu is constant, if we move n to infinity, then p must move to 0 to cancel this out. Okay, so we move n to the infinity while keeping this mu constant. Okay, in this limit, we have this converges to exponential of negative mu, and this one converges to 1. Okay, just this n just goes to infinity, so since this k is constant, this converges to 1. So this is just a formula you can look up somewhere. So in this limit, this probability distribution function converges to, wait a minute. So what happens to these terms? They all converges to 1, right? So this is actually cancelled. And this, so okay, let's see. N minus 1, n, this converges to 1. And n minus 2 over n converges to 1. And n minus k plus 1 over n converges to 1, because k is constant here. So if we move n to infinity, this converges to 1. So all these terms here converges to 1. So what's left is this. So we have this part, and we have this part. So mu to the power of k, k factorial, exponential of negative mu. So that's the distribution function for the Poisson distribution with parameter mu. So what we did here is to take a kind of strange limit. So mu was np, and while keeping this constant, we take the limit. Okay, so the probability of observing, for example, a head in coin flipping approaches 0. So it will be very rare to find a head. But we are trying infinitely many times of coin flippings. Okay, still, we are having this mu constant. But remember what this NP means in binomial distribution? It is actually the expectation value of this random variable, right? This was NP. So this mu, parameter mu of the Poisson distribution represents some kind of expectation value. I mean, it is the expectation value of the Poisson distribution, Poisson variable, indeed. So, so that's how we can understand Poisson distribution as a limiting case of the binomial distribution where the probability P approaches 0 and the number of trials approaches infinity. Okay. So in this case, we can calculate the probability generating function for Poisson distribution. So just apply the definition. So you sum over k from 0 to infinity, s to the power of k, and e to the power of negative mu, and mu to the power of k, k factorial. Okay? If you calculate this, so this is constant, so you can put this out. And we can put s and mu together because they have the same power. S mu k factorial. But this is just a Taylor series of the exponential function, right? So this is exponential of s mu. So both are exponential. We can just put them together. So mu s minus 1. So this is the probability generating function for the Poisson distribution. And from this, you can calculate the expectation value, which should be mu. You should try it. And also you can calculate the variance, which should be, actually it should be mu. Okay. You know, in the case of binomial distribution, expectation value was NP, right? And actually this is consistent with the definition of mu. And in the case of binomial distribution, the variance of the random variable was NPQ. And Q is 1 minus P, remember? But in our limit, P approaches 0 and N approaches infinity, but their product is kept constant, which is actually mu. But this term, if P goes to 0, then this just converges to 1. So after all, this converges to mu, so it makes sense. So they are actually equivalent in some certain limit. Okay. So let's see the shape of the Poisson distribution. When the parameter mu is 0.5, we have this purple line. Okay, remember this parameter is the average value or the expectation value of this random variable. So when this mu is small, the average should be small. So this distribution is kind of concentrated towards the lower values of k. Okay. On the other hand, when mu is 1, so we have this green line. So it has a little bit larger probability for larger values of k. And if we look at the case for mu equal to 10, so we have this broad distribution. And this looks much, it looks more or less symmetric around this area, 10. Okay, so the average of this value should be 10 because mu is 10, and it looks more or less symmetric around this point. Okay, so this one, this side and this side looks more or less the same. So when this mu is large, it will look more like the binomial distribution. Remember, binomial distribution was symmetric around the mean, so this will be quite similar to that. Okay, and here's another rather interesting example. So this table shows the annual numbers of deaths from horse kicks, okay, in 14 Prussian Army Corps between 1875 and 1894. Okay, this is rather old data. So in this age, they used to ride horses in the army, and sometimes they get kicked by the horse and be killed. So here's the frequency. So in each year, okay, no, deaths from horse kick. So out of 280 army corps, number of deaths observed was 0 for 144 army corps, and one soldier was killed in 91 army corps, and 2 soldiers were killed in 32 corps, and 4 soldiers are killed in 11 corps, and so on. Of course, the number of soldiers kicked by the horse to death is not so common. So it's a rare event. So it can be well modeled by the Poisson distribution. Okay, so by choosing the appropriate value for this mu, then we can calculate the probability of, okay, so this number is the random variable k here. Okay, so by choosing the appropriate value for this mu, we can calculate the probability of k equal to 0, and if you multiply by 280, you should get this number, 139. And by using the same function with different k, you should get 97 and all these numbers also. So if you compare these predicted numbers with the actual numbers, you will find they are quite similar, right? Of course, there are some differences. It's not exactly, I mean, accurate, but if you look at this uh, approximate numbers, 140, around 140, a little less than 100, around 30, around 10, around 1, and so on. The orders are in a remarkable agreement. So, this is a nice example of the application of Poisson distribution. All right.